Could you hear me? Thank you. Okay, just a small announcement. Next week we will have no lab because my teaching assistant will be abroad. So the second lab will be postponed. No, not next week, but we will have regular lectures on Tuesday and Friday. Okay, so today we have. I don't know why it's too. Let me check the microphone. It's too high. Okay. Today we have, in the first part of the lecture, we will complete the introduction to topic modeling strategies. Actually, we will see together now the most traditional established topic modeling strategies, namely latent semantic indexing and latent data allocation, LSA and LDA. And then we will see also an extension of LDA, which is called auto-topic modeling, which could be helpful for addressing specific tasks. And is also an interesting application for text mining. In the second part of the lecture, as I already announced you during the last lectures, I will do a quick refresher of neural networks and deep learning, because it is instrumental for the next part of the course, especially for the presentation of the architectures for embedding and transformers and so on and so forth. So we must to make sure that all of you have fundamentals of neural networks and deep learning. I try to quickly refresh, so it's a quick recap, not a topic, a specific detailed topic of this course. It's not the main core part of this course, but I would like just to do a quick refresh in order to also align any student who is not a data science and engineering student or is coming from abroad. So I think it's good for all of you a refresh about this topic. I will do it in the second part of this lecture. And then, of course, next week we will move to the core part of the vector-based representation of text, which is basically the exploitation of neural networks in order to build a representation of text that try to capture the semantics behind the text, not only the syntax. Okay, and of course they heavily rely on neural networks and then on deep learning networks. So of course we do need we must be aware of how a neural network is trained and is applied for the inference process. Okay, let's go back now. Here. Okay, let's have a refresh of what we have done last class lecture. The goal of latex semantic indexing is to exploit an established matrix factorization approach called SVD, singular value decomposition, in order to reduce the rank of a document word matrix. So given a text representation, occurrence-based text representation, like document word matrix, our goal is to simplify our representation and to reduce it to a lower rank. This is the general goal of dimensionality reduction, which is aimed at, for example, visualizing data more effectively, for example, in 2D or 3D plots. Or in our case, this is instrumental for detecting the main topics in a collection of documents. So we will try to leverage this kind of general purpose approaches called data semantic indexing for topic modeling. And we will see how to do this. We also try to formalize the theoretical foundations behind this. We have already started to discuss this aspect during the last lecture, and try to also to apply it in some simple examples and exercises, so that you can be able to apply this kind of approaches in practice. So what is singular value decomposition? Singular value decomposition takes a matrix A as an input, which is, for the sake of simplicity, a document word matrix, where rows are documents. Each row corresponds to a different sample, which in our case consists of a document. And each column is a feature, which in our case consists of a different word in the vocabulary, for example, English vocabulary. So we have potentially many dimensions, many features. So it's a high dimensional matrix. We can weight the occurrence of a word in a document in many different ways. We have discussed together last lecture, for example, the use of TF-IDF or BM25 or any possible variant. For the sake of simplicity, we can also consider a simple frequency count, like a document frequency, or even a one-hot encoding representation, so 0, 1, were present or not present. So here the goal is to reduce this matrix in order to simplify, to highlight what are the main topics and which are the documents that cover each of the discovered topics, and which are the words that describe these main underlying topics. So we start from matrix factorization, consisting of the product of three matrices, U, sigma, and V transposed. This is the diagonal matrix, which is a matrix consisting of 0 elements, except for the numbers in the main diagonal. In the diagonal, we have the so-called eigenvalues, which are conventionally sorted in decreasing order. The highest eigenvalue corresponds to the most relevant topic, and then the lower the eigenvalue, the lower the importance of the corresponding topic. Since potentially this matrix contains a lot of different candidate topics, our goal is to simplify, to reduce the redundancy, to focus more our attention on what is the most important part of the analyzed documents, because our assumption is that actually the analyzed documents cover many different sub-aspects or subtopics, but the main topics, the ones that are worth considering first, are typically few, not more than 3, 5, 6. So you have to transform your original data representation in a low-rank representation and try to find the approximated version, which minimizes the error. So it's the approximation. So you come up with a low-rank representation with a rank which is fixed. You have also the chance to empirically choose which is the appropriate rank to set. We will see this later on. And then we will get, after considering the original, on top of the original SVD, you can apply a transformation, which consists in reducing to 0 some of the values of the diagonal matrix So try to neglect some of the least important topics covered in by the collection. And accordingly, you have to reduce to zero also part of the other two matrices, because this is a product. So if you reduce to zero these parts are simplified. So you will come up with a so-called reduced version of the SVD. The reduced version, of course, is not lossless. So you miss some information, of course, because it is an approximation. But your goal is to simplify in order to focus the representation on the most important topics. So what you get here is a simplified version of A called A prime, which is the product of U, sigma prime, and BT. As in this part, this gray part corresponds to the reduced simplified version. So we will mainly focus on the topics covered by this non-zero part. All these other eigenvalues are reduced to zero. Okay, now how to use this kind of decomposition? This decomposition, as I told you before, is useful for dimensionality reduction in general, whatever is the application field that you wanna consider. But in our case, for our purposes, we leverage such established dimensionality reduction method to address topic modeling. So how to do this? So if each eigenvalue in A prime corresponds to a salient concept, a salient topic, we can derive also the relevance of each document with respect to the topic, because we assume, of course, we assume that a topic may cover multiple topics, one or more, or at least maybe one topic is not covered by a specific. So given a document, it may cover a subset of topics, but potentially more than one. And the same for the words. So each topic is described by a set of words. So we want to get a word level description of each topic, consisting of a selection or a short list of the most correlated words. So the words that are most related to the topic. Okay. So how to get this? You have to just simply multiply the diagonal matrix reduced version with the left and right hand side of the decomposition. More specifically, the first k rows in V transposed represent the relevance of each document with respect to the k most relevant topics, whereas the first k columns of U represent the relevance of each word. So in this way, in order to estimate, to quantify the relevance, for example, of a word with respect to a topic, and then, of course, rank the words in order of decreasing relevance with respect to a particular topic, you just have to multiply the values in the diagonal matrix, the reduced version, sigma prime, by a specific right singular vector, because you have right and left singular vectors. And I can show you graphically, it's easier to get this. So let's take a look here. We no longer consider the original version, because we will focus on the reduced one. We will come up with this simplified version where the gray part is reduced to zero. You will have here the topic relevance scores, which correspond to the eigenvalues. And here you have the eigenvectors. And for U, matrix U has rows. Each row corresponds to a different word, whereas each column corresponds to each of the k selected topics. Whereas V transposed is, again, a matrix where each row corresponds to k topics, because the product is the matrix product is rows by columns. Okay, So here you have the topics, and as the columns, you have the documents. So in order to get the relevance of the documents with respect to the topics, you have to multiply this to sigma prime multiplied by v transpose. Whereas if you need to get the relevance of the words with respect to the topics, you have to multiply this. Okay, let's see how to do this with an example. But first, before moving to the example, we need also to decide at the preliminary stage, when you have this, given this matrix, the original one, how to get this. So how can you decide in an empirical way how many topics are actually relevant? Of course, you may know this. You may get this information from other sources. You may know it in advance, and you may also devise some supervised strategies. But this is out of the scope of these techniques, which are typically unsupervised. So your goal is to take as input a collection of documents and some parameters, and then produce a list of topics with the topic descriptions. Here at the word level. There are also some more sophisticated approaches based on deep learning, which also provide you some descriptions at the sentence level, for example. But these are not covered by this lecture. Now, we want to decide how to choose the most relevant topics. Of course, the higher the eigenvalue, the more relevant the topic. We can also compare the relative importance of a topic with respect to the another. So we can sort the eigenvalues in decreasing order and look at the values of, for example, of the top ranked topic here, the ones that say here, with respect to the following one. The next one, the one in second position, will have a lower importance, but you can compare them with each other. So if the second one has an importance which is lower than the half of the previous one, it means that we can empirically neglect all that topic and all the subsequent ones. This is the empirical method. Of course, it's not always true. It's an approximation, but it's commonly applied, for example, for summarization purposes. So the empirical strategy to set the number of topics is this one. So you can find the smallest singular value, which is above of the highest one. And then, of course, if you have other strategies to choose the number of topics, of course, do apply it. So if the number of topics is given because you already know it from your application context or whatever, it's fine. But if you don't have any clue on how many topics you can get from your collection, this is an empirical way to compute it. So let's try to apply this approach using in a simple exercise. So given this simplified SVD, reduced SVD decomposition of a Word document matrix, where here you have simply the frequency counts, not 0, 1, but absolute frequency. You have this transformation, which is reduced, and you have to find the document level topic relevance scores. Okay, so for each document, you want to know, given a document, which is the relevance of topic 1, which is the relevance of topic 2. So the question you are going to answer is, okay, given a document, for example, if you have a bunch of scientific papers, which is the most significant topics? Which are the topics that are covered by that document? you have a set of candidate topics, for example, AI, robotics, finance, whatever. You have to choose to which it belongs to. You don't have a training set, so you are in a fully unsupervised scenario. You have the possibility to apply this in order to simplify the representation of the data and see what are the correlations between the documents with the underlying topics. So we can start looking at these values and applying the empirical method. You can see easily that these two topics are the first two topics are relevant because they have a relatively high value, 13 and 10, whereas the third one is just 1, so it's less than the half of the first one. So you can reduce to 0 this part. Okay, so you keep only the first two most important topics. Then we can compute the document level topic relevance. How to do this? So in order to compute a vector consisting of a topic relevance, so a relevance score per topic, you need to multiply here. You need to multiply this reduced matrix with 2 dimensions, because you keep only the first two topics, by the topic document matrix. Okay, you do the multiplication. How to multiply it? Rows by columns. Okay, matrix multiplication, and you get these results. Okay, so of course, according to this result, the first two documents mainly cover topic number 2, whereas these are the representative of the main topics. So you can also compare with each other the documents according to what is the relative coverage of a given of the main topics. Here is the approach. You have to multiply rows by columns, like R1.C1 or R2.C2, and so on. Okay, so it's a simple multiplication. This is how to exploit a reduced SVD representation in order to get a topic level representation. And then we can do further. We can go further and get some gain more insights, because we can also rank the documents in order of relevance with respect to given topic. For example, given the previous representation, of course, you can rank the vectors by decreasing value, by decreasing the second dimension, according to the value of the second dimension, because it corresponds to the topic number 2. So, of course, D1 and D2 are the most relevant ones. And then, last but not the least, you can decide, you can get a word level representation of the topic. Okay, I want to provide as an output a description of the topic consisting of a subset of words. Of course, words that occur in the document collection. You cannot provide, using LSA, you cannot provide with a rephrase of the original text, because this approach is strictly occurrence-based. We will see that later on there are generative approaches, other strategies that try to apply sequence-to-sequence model in order to build a new text, like machine translation or summarization. But this is, of course, they apply different approaches, neural network-based approaches. So how to get a topic level representation of the topic? We we have to multiply, going back here, to get word level representation, you have to multiply U by sigma, again, focusing on the top two topics. So here you have a two-dimensional matrix, and you multiply rows by columns. Okay. You can multiply rows by columns, and you get this. This. So, for example, for topic number 2, you get this. So this is the word number 1, whose relevance score is 5.9. Then word 2, word 4, word 5, word 6. So the most word 1 turns out to be the most representative word. Now we are not simply a frequency-based count. It also reflects the distribution of the word concurrencies. So it's definitely more informative than a simple word cloud. Why is such an approach so popular? Because it's scalable also. Especially when you have sparse representations, or you have representation of the original matrix which are where dimensions can be reduced. So we have a significant reduction in the original dimensions, which is typical for textual data. Like I have to focus on, I have thousands of documents and thousands of words in a document because the vocabulary is huge. But at the end, the topics I want to describe are few, and each topic can be summarized by a few mainly representative words. And this is the case for many text mining scenarios. You can find several efficient representations, even scalable ones, so implementations that work on big data architectures. So it's quite popular approach to do topic modeling, quite popular yet simple, so simple yet effective, because you can also reuse some existing implementation without rewriting the code from scratch. Okay, then any questions about the LSA? Have you ever heard about LSA? Anyone already knows? Okay, so it's quite known concepts. Okay, for those who remember that. Okay, then next, established strategy for topic modeling is LDA. LDA relies on a different approach, no longer on matrix factorization, but on probabilistic models. The idea is to represent documents as a mixture of multiple topics, where topics are probability distributions over a vocabulary of words. So a vocabulary is, of course, a large set of words, and you have to build the distributions over the vocabulary words, which describe each of the topics in the collection. Then, once you have built your own distribution for each topic, you have built your distribution over the words of the vocabulary. You can represent the documents as a distribution over the topics. because of course, you assume again, as in the previous case, as in LSA, that the documents may cover multiple topics. A topic may be covered by a subset of documents. And of course, each word can be used to describe different topics, even multiple topics. But of course, not all the words are representative of all the topics. And you can adopt here a model, a probabilistic way of reasoning, a probabilistic approach, which try to infer the optimal probability distribution, which are actually multivariate probability distributions. So here is a snapshot, a simplified representation, where you start here. For a given topic K, you need to know here you have to specify the number of topics in advance, so no empirical way to approximate it. It's a drawback with respect to LSA. You have the vocabulary of words, and you have a distribution of probability, which can be estimated in any way. For example, in neural networks, you commonly use softmax or similar functions. Here is a distribution of probability. You can estimate using some statistical sampling. So there are statistical sampling methods that are applied in order to estimate this distribution. But you will, what you get at the end is a distribution of probability distribution over words in the vocabulary for each topic, which is here, for example, is a representative of a given of an arbitrary topic K. Then you do the same for each of the analyzed topics. Then on top, once you have done this for each of the K topics you consider, topic 1, topic 2, topic 3, topic K minus 1 equals topic K, you will compute, you will infer the distribution of the documents over the topics. So you try here, as for the sake of simplicity, we assigned a label to the topics. So, for example, topic K mainly covers politics, topic K-1 covers sports, and so on and so forth. This is not automatic. You have to do it or human-driven, or you need a training set in order to classify these topics as with human-readable labels. And then you have a distribution, which is called P over these topics. For this document, an arbitrary document is associated with a distribution, a probability distribution over the topics. So, for example, here it mainly covers sports and news, whereas it does not cover economical aspects. This is a generative model. This relies on the generative model, which mainly are in charge of computing these two probability distributions. Each word is generated by sampling a topic from a document-specific distribution of topics, and then you also sample a word from the distribution of words characterizing the topics. So you do some statistical sampling in order to estimate which is the optimal probability distribution. You typically start from a random or pseudo-random setting, and then after the many iterations, the statistical sampling process will converge to the optimal one using these conjugated priors. These are established functions which are derived from the Bernoulli distribution. Bernoulli is typically defined for discrete variables. There are also continuous versions of the discrete Bernoulli distribution. One is called the beta distribution. Beta distribution can be extended also for the multivariate case. And the Dirichlet prior is likely an extension of the beta distribution, basically. So it's a more mathematical aspect, which is how to formalize this statistical inference process. This is a well-known problem, not mainly related to the machine learning field, so it's more for mathematicians. You have some approaches in order to do statistical inference by trying to optimize it. So there are some expectation maximization functions which allow you to iterate and infer the distribution appropriately in a reasonable computational time. Of course, this task can be extremely computationally intensive, so you cannot scale towards big document distribution because the problem is not scalable at all. But especially when you have small or medium-sized document collections, it can be, and you already know in advance the number of topics, you can achieve satisfactory results. Okay. So what you need as an input is a vocabulary of words, a fixed set number of topics, and two parameters which are the parameters of the Dirichlet prior that need to be optimized. One is related to the distribution of the words of the words over the topics, and the other is related to the distribution of the topics over each document. More specifically, this is the first one, which is related to the word, which is conditioned on the topic and on the parameter beta. The second one, which is alpha, is related to the document level, the document distribution. So you find the right hand side figure. So this is to estimate this part. This is for this. So okay, this is the left hand side, the right hand side part, and this is the left hand side. So here is a representation of the generative model, which is a standard way to represent this kind of generative approaches, which are mainly approximations of joint multivariate distributions of probabilities over the topic mixture. So what are the parameters? Here you have a corpus size. You have a number of topics, which there was K, and here is N. You have the joint distribution over the topics, and you have the set of words. Of course, you have to repeat this for any topic. If you have K topics, you have to do it separately for each of the topics. And then you have to apply statistical sampling over the documents. So again, if you have so many, it scales with the number of documents, because if you have a very large collection of documents, this computation becomes almost computationally prohibitive. And here are the formula for the computation of the probability, which is basically entails estimating a multivariate distribution, which is derived from the previous one. And you have to sum, of course, over all topics, because you have to compute separately per topic and then integrate over the distribution in order to get the joint probability distribution, which is the composition of the marginal ones computed separately for each document. Okay, here you have some implementations of this approach. These are less scalable than the previous one, so the complexity is higher, especially with the number of documents. Some of the most effective implementation is in MATLAB. You need to specify the parameters alpha and beta, so you need to tune the parameters in order to achieve satisfactory results. If you wanted to learn more, especially for the mathematical point of view, I suggest this additional reading. And we can see immediately an application of this kind of techniques, which is more practical and related to a particular field in the NLP, which is the analysis of scientific papers, scientific data. The model is called the author topic model, and it is also quite general, so it can be applied also to, it's portable to other domains, not only for scientific academic papers, but it works also in other similar domains. This is basically a generalization of the LDA model, which can be particularly helpful for doing topic modeling in some practical context. What is the idea here? The idea is to add a third dimension. So currently in the LDA model, we have considered documents, words, which are correlated with a subset, a given predefined number of topics. Now we add the third dimension, which are the authors of the documents. Okay, if I am the author of a document, for example, if I co-authored a scientific paper, I want to know which are the topics on which, so if I'm an expert, if I'm proficient on some specific topics. Okay, so based on my relationship between the documents and the terms occurring in the documents. So the questions that we would like to answer are the following. So who is the most authoritative author on a given topic? Let's assume to have a bunch of scientific papers, for example, those indexed in Scopus or in PubMed. We are the European Commission. We need to award some short list of scientists who are in charge of doing some advanced research on some topics, for example, genetics or whatever. Who are the most authoritative authors, scientists on a particular field? Could I answer this question just looking into the content of the paper? Not yet. We need also the authorship information. So we add an additional dimension which tells you, okay, you are the author of a paper which covers that topic. Then, of course, if you have this approach is still simplified a little bit, because we assume that you are an authoritative scientist if you have published many papers on that topic. This is not always the case, because if I publish a lot of garbage papers, I am authoritative according to this model, but of course I'm not. So it should be better also to add a fourth dimension, which are, for example, the citations. The H-index is an index score used to evaluate the quality of the researchers according to the citations. So I have a paper, H-index equal to 10, meaning it means that I have at least 10 papers cited by more than 10 other works. Okay, this is a further extension which is not covered by the author topic model. But we can start here simply looking into the document content and the document authorship. Okay, so this is the first step. You can also extend and revise the model and apply it, move it to other similar contexts. So we can also look at the specific author and decide, okay, which are the topics covered by the works published by Luca Cagliero. I look into the documents published, I check the content, and I try to figure out which are the most salient topics. And then, which is the most authoritative paper of an author? Again, you can consider citations, which are an external source, or if you don't have the citation information, you can look into the papers and relevance of that paper in a collection according to a given topic. So how to formalize this problem, which is a generalization of the previous one? You have a document which consists of also a set of words, and the words are chosen from a vocabulary. The author is associated with the authors are associated with the documents. So, for example, the document is authored by one or more co-authors. And so you have these pairs, word author, which represent a given collection of documents. You can try to infer a multinomial distribution over topics for each author, a multimodal distribution of words for each topic. This part is already accomplished by the LDA, the traditional LDA model. And you can, of course, assume that an author with a document with multiple authors can be modeled as a distribution over topics, as in the LDA case, which is also mixed distribution of the authors. So it's authors who have different expertise, maybe complementary expertise, can contribute to in the writing of the document. Of course, here, for the sake of simplicity, this model does not distinguish between the primary author, the first author, the main author, the secondary authors. Okay, here we neglect both citation information and author contribution, description of the author contribution. Here is the representation where you basically add this. This is the new part compared to the LDA model, where you have the distribution of the authors of the topics, and the levels of inference start again from the word. Then you infer the distribution of authors over topics, which is new, and then you try to combine this, and of course you have to iterate this model. Of course, in this model, of course, the complexity of the statistical inference gets worse because you need to further explore even the authorship dimension. But it's quite interesting and appealing for a number of different real world applications. Here is the reformulation of the previous sampling strategy for statistical inference, by also considering the A dimension, so the authorship dimension. These probabilities are just reformulations of what comes from the original LDA model, so nothing new actually. Anyone sees applications or relationship with some known models or practical use of this kind of models? Have you ever heard about this? Yes? You already applied this to some? Okay. Okay. You have not applied for topic modeling, I assume. No. I just know. Which implementation have you used? R, MATLAB, or? No. But I know the concept. Oh. Okay. Okay. Good. Okay. During the lab yesterday, Moreno has already proposed you to apply some LDA and LSA models available in Scalearn. Have you already tried to do it or not yet? Because I know that the lab is quite long, so it may take more than 3 hours to be completed. Any one of you has already completed the laboratory, also the topic modeling part? No. Okay. I recommend you to complete it before the end, before the next laboratory, just because it's I think it's definitely more useful to see how this system works in practice, not only on from a theoretical point of view. So since it is already available there in the practice text, you just have to simply try to play with the system, try to configure the parameters and see what are the results on some simple examples. So I recommend you to try to use them in practice. Of course, you may have the chance to also explore these solutions for the project work, but of course it depends on the topic of your project work. So maybe it's better if you try to use them immediately after the theoretical lesson, of course. So if you have the time and if you have the chance, I recommend you to finalize the laboratory practice. Okay, let's move to the neural network recap. Our goal here is not, of course, to do a course on deep learning. My goal is not to teach deep learning now. My goal is to just quickly review some of the fundamentals and, of course, put the emphasis on what the main properties related to textual data, for inference from textual data are. So I wanna emphasize the aspects that are crucial for applying neural network learning to textual data. Of course, we need some basic fundamentals. Of course, I'm pretty sure that most of you already know this, at least for those who already attended the data science and engineering courses, but not all. Maybe some outgoing student or some students who come from other courses have not attended the deep learning course yet. So I want to spend just at most a couple of hours to recap these concepts. Then, of course, from the next week on, I will assume that these are known concepts, and we will start with the presentation of the text representation techniques based on deep neural networks. So if you have questions, if you need, of course, further help to bridge the gap for specific theoretical aspects related to deep learning, please contact me. We can provide you with additional materials or books in order to help you to better understand these concepts. I have reused some of the materials available as supporting from deep learning MLT course. So it's I think it's quite clear because they use many graphical representations. So instead of going into the details, which are of course out of the scope of this course, I try to summarize the key aspects and help you capture what are the key points related to NLP. So my goal is to stress on the importance of some particular architectural properties, neural network architectures properties related to natural language processing. So, of course, we already know what is the difference between deep learning and machine learning. Mainly in traditional machine learning and classification field, you have to explicitly define your features describing your data. So you rely on handcrafted features. And we have already seen this by talking about the traditional pre-processing step. So how to represent the text, you have to envision what are the features that are likely represent your data at best for your purposes, and then apply some supervised stage of classification or regression. This is commonly done in machine learning. When you talk about machine learning, you typically think about supervised problems like classification or regression, whereas all the descriptive parts of the data science field, like clustering or association mining, are commonly mentioned as data mining algorithms, which is the difference is very, very small. So they are actually teached together. So often when you attend the machine learning course, typically they present both. The attention of the research community has focused mainly on neural networks for specific types of data. For example, since the 60s or 70s, researchers have mainly focused on neural network learning for coping with, for example, images or videos, because in that case, it was really difficult to capture relevant explicit patterns. So in a text, probably in some cases, not the complex ones, but in simplest cases, you are able to explicitly define which are the properties. So you are able to read, to define some syntactic features or some word level features where, okay, you have the feeling of what is really going on, because you can understand, you can figure out which are the words that are more relevant to a particular aspect, to a particular sentiment. You are able to distinguish between positive and negative words. You are able to filter out words that are irrelevant, like prepositions or articles. Whereas when you have to cope with other types of data, like images or videos or audio without a transcription, textual transcription, it's harder to define explicitly the features. So not always the case if you are able to effectively perform handcrafted feature engineering step. So in that case, the research community has focused on deep learning first, trying to devise some neural network-based approach, which starts from very simple networks like feed-forward neural networks, and then moving to more complex architectures, even with a higher number of layers in between the input and the output. So what is the key difference between machine learning and deep learning? Is in deep learning, you rely on more complex architectures with many intermediate stages. And typically, you do not, you try to leverage the neural network in order to infer what are the potentially irrelevant features automatically. So without the use of automated handcrafted features. This is the common approach for deep learning. What happened in the last decade is that this kind of approach has become also established for natural language understanding, because the research community has developed and designed and tested some extremely effective ways to represent textual data. They started from word level representations. The most established one was Word2Vec. I will present this solution next time, so next week. We will have a lesson focused on word level embedding. Then they try to go on and try to embed the textual representation into vector representation derived using neural networks for sentences, for paragraphs, for entire documents. So they have found out a way to leverage such an approach in an efficient and yet effective way. And this is, of course, mainly due to the advance of the research field. So the new researchers that have new ideas and they exchange new solutions which are proved to be effective, but also the advances in the technologies, so more powerful hardware, more powerful GPUs, which allow parallel computation, which allow to reduce the computational time and memory required. So they have the chance to explore solutions that are not affordable 10 or 15 years ago. Okay, so I have already mentioned these aspects. I don't want to spend too much time in aspects that are, of course, well known. The building blocks of neural networks, I suppose that all of you are aware of this, but if not, let me just briefly mention. You have a set of inputs, you have a set of weights, which are combined, typically using a summation function, and then you can apply a nonlinear stage to transform your combination of inputs using a so-called activation function. The activation function introduces nonlinearity in your model because it's quite uncommon to effectively solve a real-life problem using a linear model. Linear models are very simple, are fantastic. If you are able to achieve good performance in linear model, you are lucky. But unfortunately, this is not the case for most real scenarios, especially when you have multivariate cases, so multiple variables that need to be combined together. So practical, the real world is nonlinear, unfortunately, and the linear is just a simplification which holds in very few cases. The linear is commonly a baseline. So if you are not able to improve the performance of the linear model, probably you are not so smart. At least your solution, your architecture is not very effective because the linear models are commonly not the best solution. Okay, you can also, okay, in the formulation of the feed-forward network, which is very, very established, this is a quite old-fashioned style representation. You also have this term called W0, which is called bias, and it is a constant term which can also be depicted here as a 1 because it's not an input, exactly, it's a constant term. Then, okay, the formulation can be written as a linear combination of these two terms, of the inputs and the weights. You have here the dot product between these two. And then you apply an activation function. The activation function depends, of course, on your application. Of course, some of the activation functions are more effective in some cases, some other. So it depends actually on the domain. It's not there is not a unified solution. Some activation functions are popular, more popular than others, especially because, for example, the sigmoid function ranges between 0 and 1, which is a quite good property, nice property to have because you have like a probability. And then there are other distributions which can be also applied to solve specific issues like ReLU or hyperbolic tangent. Nonlinearity is one of the key steps needed in order to make the models competitive against state-of-the-art approaches. Because the world is nonlinear, because when you have to accomplish a supervised task, you need to, as you know from the basics of machine learning, you need to build a decision boundary which separates the samples belonging to different categories, different classes. And the boundary is unlikely to be a simple line or a simple plane. You need to apply some more sophisticated nonlinear activation function in order to at least approximate a nonlinear boundaries. Okay, here is the computation we can skip. This is a simplified version of what we call what we denote as the unit, the fundamental unit of a neural network called perceptron, which in the old-fashioned style is it mimics the human brain, so the neurons in the human brain. And this is the unit which can be replicated, and the neurons can be combined together, like in a brain. And each perceptron computes allows you to do this to apply the activation function and to compute this value, which is the combination again, the product here, the dot product. You sum the bias. You apply the activation function. You sum the bias, and you get Z. You can replicate this process by feeding each node, each perceptron, with the inputs in a dense layer. A dense means that you have all the connections. There are, of course, non-dense architectures where the connections are not fully connected. Dense and fully connected are synonyms in this context. And you can, of course, generalize this, because you may have many neurons here, Z1, Z2, Zn, and here you have the formulation which is similar for all the cases. You can also have multiple outputs, not simply one, depending, of course, on the target of your application. The outputs are here denoted as Y. You have Y1, Y2, and here Y is computed just simply applying the activation function, which gives you the nonlinearity to your solution. Here is a representation of a fully connected neural network with just one intermediate layer. So this is the intermediate layer. The layers, if the layers are more than one, we will usually talk about deep learning networks. When it's deep when you have typically more than one layer. Is it always useful? It depends, especially, for example, for NLP. The most famous architecture that has been proposed for word-level embedding, as we will see on next Tuesday, is called Word2Vec, and is not a deep network. It's just one layer. Okay? So it depends. Of course, doing more sophisticated, more elaborated learning and inference process could help, but it also depends on the kind of network you have designed, or that depends on the amount and quality of the data you can provide as input to the network. So it's not obvious that it's not always the case that deep networks work with many layers work better than simpler networks. There are even scenarios where you have a lack of training data, or even you are in the absence of labeled data, or when there are scenarios where you are capable of explicitly defining your features in a way that is easy to approach, for example, using different strategies like using associative classification, Bayesian networks. So it's not always the case that neural networks are the best model, especially when you have to when you need some additional properties, like, for example, interpretability. There are models that inherently provide you with interpretable solutions and models, so that explain you why the reason behind the prediction without the need of adding additional steps. So neural networks are not always the best of all the options. You need to carefully check before adopting these solutions. Here is a notation used to indicate the layers for a deep network, and this is typically indicated for fully connected layers. So how to apply this this network? You can simply, given a test set, you take the values of the features associated with the test sample, and you apply to perform the inference. The inference means that you pass the input values to the network. You do the computation for the intermediate stages, and you do the prediction. Of course, since you are when you are training the network, the label, the actual label of your sample is known. Whereas when you have to do inference of a test sample, this is typically unknown. So you want to classify a new unknown sample. So when you do training, you try to leverage what you already know, your prior knowledge, and typically you do this by computing so-called empirical loss. The loss is the gap between prediction and actual. Of course, the higher is the loss, the worse the performance. So you need your network need to refine its reasoning. The loss can be computed in many ways, but basically it's a function of the weights. It depends on the weights of the networks, which are currently set up, and is a function which combines, which computes the difference, the gap between predicted and actual value. This is the prediction, the current prediction for the ice sample, and this is the actual prediction. Of course, the weights need to be set properly in order to minimize the loss. Our goal is to minimize the empirical loss, which is, of course, average over all samples, where n is the number of samples used in the training phase. So the lower the empirical loss, the better the more robust is the better your model. There are different ways to compute the loss. You probably already know it's a well-known theoretical concept. So you have cross entropy, you have squared error. So there are different solutions which are, of course, depend also on the kind of network you're going to implementing. When you need to optimize the loss, this is the formulation of the optimization problem, which means finding the best setting for the weights of the network in order to minimize the empirical loss. Okay, so you find the optimal, let me say, combination of weights. What does it mean in practice? In practice, it means that since the empirical loss is a function of the weights, given the values of the weights, you can plot this empirical loss value here as a function, which in a 2D space, if you have these two dimensions, to the sake of simplicity, two weights, W0 and W1, you will have this surface, which shows some minimum and some maximum, some local minimum and some local maximum, and also you want to achieve, of course, in theoretical speaking, you like to move towards the global minimum, okay, which is the point which corresponds to the configuration in terms of weights, W0 and W1, which achieves the lowest empirical loss. Of course, this is a simplification because the weights are so many not only 2, and it is not so easy from a computational viewpoint to move towards the global minimum. So even achieving a local minimum is complex. So you have to navigate this surface, which is actually not smooth. You have very complex representations like this. So, as you know, this training process is a nightmare in many scenarios. So this is very extremely complex to find this peak of minimal loss compared to a lot of other scenarios where, of course, the configuration is not so good. So going back, our goal is to navigate through the surface of the weights and to find the configuration that, or at least converge towards a good configuration, at least a global minimum, local minimum, optimizing this function. So the idea is to start from a point, a random point, or pseudo-random. You can decide what is the starting point. But then you compute the gradient of this function, which tells you the direction towards the increase of the loss, which is not the right direction, of course. So you need to go in the opposite way. So you have to descend the gradient. Okay? So you go a step towards the opposite direction of the gradient. So you go towards the minimum, at least theoretically speaking. You have this step, which can be also very small, and you move towards the minimum of the gradient. And you repeat this until you are at least satisfied. Okay, you have this process, which is well known. It's called the gradient descent, and tries to iteratively update the weights of the network. In order to compute the gradient, you would need to explore, to read, to analyze all the samples in your training data, which is practically unfeasible. Okay, so typically you do not consider in the optimization process the whole set of samples, but only a batch, a subset of samples. Okay, this batch is can be a parameter, so it can be larger or smaller, but is a subset of samples that I consider in order to refine the computation, to make the computation of the gradient more efficient. And then you follow this line, and you apply the so-called backpropagation process and try to optimize the weights according to the gradient. So this is a partial derivative with respect to these weights, which can be combined together. So I skip the theoretical aspects, which are, of course, not out of the scope of this course. And you need to repeat, of course, this for every weight in the network using the gradient descent. Okay? Okay, here is just the summary of the complexity of this computation, which tells you, okay, please pay attention because the optimization is NP-complete or even worse. So let's keep it simple. You also have a rate of updates, which is called the learning rate, which need to be set, and it tells you what are the steps needed, what is the size of the steps towards convergence. And what happens is that if you do longer steps towards convergence, you may incur in some errors because the the system in the learning curve may do some mistakes. For example, if I have, let's see, if I am here and I do very small steps, I'm not sure to achieve a good, the optimal convergence. So it may happen that if the learning rate is low, I will not achieve the local minimum. Whereas if the steps are too large, I may skip the local minimum and go outside. Okay, so you need to optimize, to tune the learning rate. This is typical hyperparameter that you have to tune in order to, and also the batch size, in order to properly configure your system according to the training data. And you have to explore the scenario in which you have to apply your network accurately. Okay, there are, of course, more advanced solutions for this problem, which is very, very well known. So it's not a new problem. The ways to solve this issue can be, for example, do adaptive learning rate, so change the step according to the intermediate feedbacks. So adapt in a flexible way, in an adaptive way, the learning rate. Okay, this is already known. So I told you that this computation of gradient descent is very complex. It's typically one of the most established way to compute it is called the stochastic gradient descent, and can be computed typically on a batch, not on the whole training set. It, of course, again, the batch size can easily affect the performance of your model as well, because if you consider a very small batch size, you may misclassify. We are not sure that the samples in the batch are actually representative of the whole collection. So you need to, let me say, balance between efficiency and effectiveness, because of course it is always a compromise between complexity and effectiveness. In some cases, your model do not ideally fit your data distribution, but as if not properly configured, is affected to underfitting or overfitting. So it means that the model is, in the case of overfitting, tends to be too complex to align it to the training data, and not general enough in order to capture general complex patterns. Because the problem is that you have no guarantee that training samples are exactly like training samples. So the variability in the sample distribution from the test from the train to the test, this variability may produce some misleading learning achievements in the learning phase, because your model can accurately fit your training data. You can design your decision binary in a very accurate way, but then the actual distribution of the data in the real world can be different. So you are not able to generalize enough, to be general enough in order to properly describe, to properly detect general patterns which work well in the real world. And the reverse, conversely, when you have a model that is too general, not specific enough, you miss some important patterns. You apply something like a linear model or very simple but not effective model. So making it simple is not always best, because in some cases you do not achieve good performances, and maybe in some cases your model misses important information, is not competitive against standard classification model like probabilistic or decisional rules. There are, of course, techniques in order to make the training process more robust. One of those is called dropout. It means setting the activation to reducing to zero the activation of some nodes in the network in order to make the learning process more random and not tightly fitted to the training data distribution. So you switch off some of the nodes using setting the activation to zero, like here, and the drop out rate is a parameter, so it can be 50% or less depending on the context. And this could help, especially when you are incurring in overfitting. There is also the possibility to stop the training phase early. This is probably what you did if you have already played with these neural network systems. So you start training your network. You look at the trend of the training loss and of the test loss, and something strange happens because okay, you keep improving the performance in the training set, but in the test, once you have achieved the steady state, you may worse the performance because the model was not trained on the test on the training set, was not capable to further improve the performance. So you have to stop early. You have to decide how at least at which stage you are. It's more convenient to stop to avoid wasting time in computation without significant improvements, but also to avoid worsen the performance, because you may get at the end in the test set worse performance. Of course, the common way to proceed is to adopt not only a train and test, but also validation set. This is also common in NLP task, especially for those who have a large availability of data, of training data, because you will typically do the trainings on a subset of labeled samples. You do hyperparameter setting on a separate validation set, and then you test your system on a set of samples for which you assume not to know the sample labels. Okay, so we can have a break now, and then in the second part we talk about recurrent neural networks and models that try to consider the sequential order of data into account, which are the core part of NLP neural network-based models, because of course text have peculiar properties that need to be considered. So see you in 15 minutes. Okay, let's start again. Now we are going to complete our neural network recap. We have already overviewed what are the fundamentals of neural network learning for feed-forward neural networks, which are the very traditional ones. There are networks that are more suitable for managing, for handling sequential data. So what sequential data are? Sequential data are data that or have intrinsic ordering of the samples, like a time series or a series of a time-stamped series of measurements, like temperature measurements acquired by a sensor, like the prices of a stock in the financial markets, the sound, the audio track of a speaker, or a piece of text. So why is the sequential data relevant to our purposes, and why networks tailored to sequential data are relevant to our purposes? Because textual data are inherently sequential. So we have a sequence of units, of textual units, which can be, in the simplest case, characters, or in the most common case, words, or even further, even more complex textual units like n-grams, sentences, or even paragraphs if you want. So you can model text as a sequence of units, as similar to other contexts like sequences or genetic sequences, or sequences of genes, sequences of proteins, sequences of temperature or measures. The key property of the text is that it is a sequence of discrete symbols. So we can distinguish between time series, which are typically a series of measurements which are described by a continuous variable, like a function, the pressure or the temperature or the humidity. These are continuous number, and we typically sample the data using some. So for each sample, you have a measurement and a timestamp. This is a typical case of time series. We can transform this numerical, this continuous series of values into discrete version. Okay, so a discrete series of temperature measures can be discretized as temperature high if the temperature is more than 25 degrees Celsius, low if it is lower than 10, and so on and so forth. So you generate some discrete symbols first, and then you map each sample, each measured sample, to a discrete symbol. This transforms a raw time series of continuous value into a discrete time series, which is also called a temporal sequence. The text is more similar to a temporal sequence of discrete values, because each textual unit, like a word, can be mapped to a symbol representing a high temperature, a low pressure, or whatever. Okay, it's a sequence of discrete elements. Now, what really matters here is the importance of the ordering of the sequence. So the fact that time matters in how you learn and how you do prediction. Why is it important? Of course, it is easy to understand, because if you have to do predictions of for example, of the future trends or the upcoming values of the series, like for example the price of a stock in the next 2 hours, you need to consider, you may consider only the current value, so the current state, and it is very complex because you have to get a snapshot of the financial market now and decide what happens later on. Or you can get a snapshot of the current and historical market state. So see what happened in the past, what's happening now, and according to the comparison and the analysis of the historical trend, you can do some forecasting. Okay, this is complex as well, but it's more technically speaking, is more reasonable, is more sound. Okay, so in some cases, when you have a natural sequential order of your samples, it's definitely more reasonable to consider the sequence of the data in the learning. So to push the sequential structure of the data, the inherent sequential structure, deep into the network learning phase. This is what we do with recurrent neural networks, that I'm going to briefly summarize, to briefly describe it here in my neural network app. So if you know what happens before, you can estimate, you can approximate the trend and say what is the direction. This applies to many different fields, including audio, including physiological time series analysis, market data, genetic data, and also text. For the text, of course, you can model the problem in different ways. What you have, for example, you have an input and one output, like this is called a one-to-one classification, like, for example, sentiment classification, sentiment analysis. Sentiment classification can be focused on a single item. So you have a sequence of items, like a sequence of textual units, like a sentence composed of a sequence of textual units, and you have to say whether that class is the class is positive or negative. So the sentiment is positive or negative. This problem is can be casted to a so-called many-to-one problem, because you have many inputs, which are the textual units, and one output, which is the sentiment score. If you have just one input, so one unit including all the text, for example, or one single word, you move to a simplified one-to-one problem. What is the advantage of getting separate inputs? Of course, you can process them in parallel. What is the key limitation of such an approach whenever you do not rely on recurrent models? Is that you neglect the temporal correlation. So the inputs here have an order, or sequential order or temporal correlation. So because here the input has a natural ordering of appearance, so the words are not ordered randomly, but they have a natural order of appearance which depends on both the syntax of the language and the semantics behind the text. So you can leverage the ordering, the positional ordering of the words in the learning phase. And this is exactly what we do with recurrent neural networks. So these are inputs that can be either independent or dependent. And you have to force the network to leverage the dependence, which can be due to the temporal relationship, like a temperature measured yesterday is likely to be related to the temperature measured today, because there are two close days, two subsequent days. Or if the words appear within the same span of text. So, for example, if two words occur within the same sentence, they are likely to convey a related meaning. So they are likely to be correlated in some sense from a semantic point of view. Then there are also situations where you have to address, to cast the problem to a one-to-many scenario, where, for example, you have an image which can be, actually the image can be also decomposed in different inputs, but okay, let's assume for the sake of simplicity that you have an input, and you have to generate a text. If you have a generative process where you have to generate new text or to rephrase a text, the outputs are not single output, but you have many outputs, one for each item that you have that composes the output text. And finally, the machine translation. Machine translation is already, I already mentioned it, that it's a problem that need to be addressed and formalized as a many-to-many, as a sequence-to-sequence problem. So you take a sequence of an input, which consists of a piece of text in a source language, and then you get a sequence in output, an arbitrary length sequence of textual units in output, written in a target language. This is a many-to-many problem, and is similar from the point of view of formalization of the task, is similar to text rephrasing. So if you need to rephrase automatically a text from a formal, from an informal to a formal, or to rephrase the text by removing also non-inclusive forms or misogyny or hate speech, you can produce an alternative version of the source text, including some variants, some corrections, which reflect, for example, the data you use to train the model. Okay, so let's go back to the perceptron we already know, and let's see how to leverage the temporal information. This process is commonly called backpropagation through time. So you leverage temporal information, which is actually which in the case of text, which is exactly as the ordering, the natural ordering of text. Because if you write, for example, the text, the written text is written from the left to the right in Italian and English, or from the right to the left in Arabic, or whatever. So you have some dependencies which are related to the sequential nature of the text. Okay, let's assume that here you have a dense layer. This dense layer is summarized here with a simplified notation as a green square. Then, given the inputs at time step 0, 1, 2, t, you will get the output. Of course, you can process them separately, disregarding the sequence of values coming before and after. The function you can formalize as something that is output at time step t, which is the function of input at time step t. But of course, if you go further, if you want to leverage what happened before, the idea is to model a state in a memory which takes the past values, what happened in the past, into account. This is called memory, and here reflects what happened at time t-1 or even 4. So the memory is updated and is used to consider the past information. You can rewrite the model as follows, where you have a recurrent cell that tries to exploit this past memory state in order to improve the quality of the process of inference of the output at time step t. A recurrent neural network is a new family of architectures which are now very well known. It's not a recent architecture, which applies at every time step a process that involves both the input, the current state, and the old state, which is the memory state, using, of course, the same function and the same parameters. So it's not like updating or re-optimizing the parameters every time step, because it's computationally infeasible. So you have a state which is updated. You update just the state using the same function and the same parameters. But of course, you have a more informative, an additional input which takes sequential historical data into account. Okay, what is the possible implementation? One of the possible implementation of this f, the function with weights. This is a function with weights that combines inputs and old states. A possible implementation is this. This is not, of course, the only possibility. There are also variants which are, of course, out of the scope of this lecture. And this is how to update the HT according to the previous, the current state and the previous old state. So you basically have a linear combination of weights, and you apply a function which is here used to combine the two. Okay, let's go further. You apply the same matrix every time step here using a so-called forward pass, and you refine the computation. So this is just another way to graphically show the key step of the recurrence process. Okay, so in order to model our sequence, we have to cope with some issues that will be particularly relevant for handling textual data. So when we have to cope with textual data, we must be aware that text composed of variable length sequences, because even if you have two pieces of text which are one a translation of another or one a reformulation of another, it is not reasonable to assume that the two pieces of text have exactly the same length. So, for example, in other scenarios, like, for example, the analysis of IoT data, maybe you have a device which is collecting measures, which is transmitting physical measurements at a fixed time frequency. So, for example, every 30 seconds or every second, and you can assume, except for some errors or missing values, that the number of inputs, the number of elements in the sequence is fixed. Because if you have a time span of 10 minutes and you have one sample per second, you can multiply 60 per 10 minutes, and you have 600 samples fixed, except for some missing value or connectivity problems. Here, this is not the case for textual data. So there are scenarios like, for example, machine translation, where you do have to handle variable length sequences, either in input or in output, or even both. So even a combination of the both, because there are cases where you cannot assume any constraint in the number of expected inputs. There are also problems related to the dependency between units, because what you see in the past is likely, what had happened in the past is likely to affect, to some extent, what you will see in the near future. Of course, who knows what near means? So is the past value I saw 10 minutes before relevant to do forecasting or not? Is it sufficient to consider an historical window of 1 day, 1 month, 1 millisecond? It depends. It depends on the application. So you have to rely on historical data in order to estimate a trend, in order to find some correlations. For example, you can apply some autocorrelation function in order to find some periodicity, some seasonalities, or some properties of the series. But at the end, you may incur in some problems, especially when you have longer sequences or like longer pieces of text. For example, I can show you an example here. Yeah. Okay, let's take a look to this. France is where I grew up, but I now live in Boston. I speak fluent French. What is the key relationship, the key term dependence that I would like to capture? The dependence between the target word that you want to predict, the output is this word missing. This is the target of our prediction, and the context. But the context is what we define as the previous word, not only the immediately preceding word, which is speak fluent, but also the preceding ones, which correspond to the history, so the historical values, not the current, but also the past ones. How long must be the time window I should consider in the analysis? Okay, here is pretty simple because, okay, in textual data you also have the structure. You have the structure of the text, you have the sectioning, you have the paragraph. Probably here it's not difficult to decide how long the time window, the historical window should be. For example, because here I have the starting of a sentence, I may split the text into sentences and then process sentences separately. This is a possibility, but it's not the only one. Please. Just one thing. The key problem here, the most challenging task, is to find the correlation between past words and the target. Now, if you look for correlations between pretty close words, like for example Boston speak, this task is definitely easier for recurrent neural networks. Whereas if you have to find some dependencies with far away words, or like samples collected many time ago, or in this case, words that are relatively distant from the target one, like French. This is extremely complex. This can be challenging. The problem is called long-term dependency, which is one of the main problems of recurrent neural networks, which are partially solved by, but not entirely solved by some more recent architectures called long short-term memories. Please.
Why French? I grew up more important than now I
No, the target is French.
Okay, because I speak fluent, but if I live now in Boston, can I speak fluent English? I grew up is more important than now I live.
Okay, I got the point. That's a good question. Okay, no. Okay. Yeah. Yeah. We don't know because we don't have the answer. Tonight you cannot sleep, so we can. Yeah, you're right. Yeah. Okay. Very good question. Any other good questions? No, please. Okay. Okay. Next. So these are the issues that need to be addressed. One is variable length sequences, I have already mentioned. Another one is long-term dependencies, is that one. The other is to take, to maintain the order, the information about ordering. And finally, you have to share the parameters, so you have to decide how to do backpropagation through time. So let's take a look to the solution now. A sequence modeling problem is the typical sequence modeling problem is called this is commonly addressed by a so-called, as we will see, forward language model. So given a piece of text with so composed of a sequence of textual units, you want to predict the next one. This is also a typical problem for generative text models, when you have to generate a new text, like a short headline of a text or an answer to a query to a user, for example, for a chatbot, for AI chatbotting. The problem is, okay, I have a piece of text which is incomplete. I have to predict which is the most likely word that comes next. And you can compose the new piece of text, new text, by just combining new small pieces of new additional units. So this is the green one is the context. The orange one is the what you want to predict. Of course, you need in order to solve this issue, you need a vector representation of text, which will be the core part of the next lecture. This consists in a way, alternative way to represent pieces of text as numbers, as vectors of numbers. Each this vector or number can be provided as input to a network, which then provides as output the vector representation of a predicted word. So we will see how to model this particular aspect next lesson on Tuesday. So the idea will be to transform the text in a way that would be suitable for doing network learning. And what we want to do is to combine the effectiveness of neural network learning in capturing inherent data correlations and their ability, as we will see, to capture semantic relationships, which are fully neglected by occurrence-based text representation like TF-IDF, BN25, one-hot encoding. So we want to learn using neural networks some representations that try to retain some semantic properties of the text which are conveyed by the original text and need to be somehow maintained in the encoded version. Okay, so okay, this is the problem of variable length sequence. This is the long-term dependence. The order, okay, the order is another big issue, because even if you don't have to cope with variable sequences of units, even if you don't have dependencies which are between textual units which are relatively far away, you may incur in problems like different sequence order. So let's take a look to this example. The food was good, but not bad at all. The food was bad, but not good at all. The words appearing in the text are exactly the same. Okay? Same words, but the meaning is completely different. This means that it's not enough to collect and combine the words in a sequence, but you need the order of appearance of each unit of text actually matters. So this is the propagation, the back propagation process that we have previously described. We will extend the process of back propagation through time using a propagation of the parameter for the updates of the weights of the networks. This is also dependent on the time. So as in the case of a simpler feed-forward network, even in recurrent neural networks, we have a solution that tries to propagate backward the information for the weight updates, even for the past states, as you can see here. And this is, of course, compulsory, because otherwise you miss to properly keep the neural network state updated according to the new samples that are coming and that are processed in the training phase. So even the gradient descent procedure is updated because it has to take into account the history, the historical, the old states, which are neglected by the traditional multi-layer perceptron architecture. If you have many steps if you have many time steps, what could happen is that the propagation through time of the gradient could be biased due to the fact of an explosion of the gradient, because of course the propagation is perturbs the distribution of the weights, and this perturbation this propagation is stepwise until the oldest history. And what could happen are two critical aspects. One is less common, it's called the exploding gradient, which means the gradient is getting bigger and bigger. And the other, which is the converse, is vanishing gradient, which is actually more and more common in our situations, which is called vanishing gradients. So if you have values of perturbation of gradient less than 1, then you have the influence of the perturbation becomes negligible for the older states. So basically, this is strictly correlated with this is correlated to the problem of long-term dependency, because again, the states that are not what is the distance from the current state is not really affected in the process of learning. So in order to mitigate these aspects, which are mainly critical, the main critical aspects are vanishing gradient and long-term dependency. The solution is called is a new architecture, which is called long short-term memory. This architecture relies on a variant of the recurrent neural network. It still belongs to the family of recurrent neural networks, but it comprises some gate stages where you have a more complex reasoning, a more complex elaboration of the state, so you can retain some information throughout the time steps, and you avoid, you partly prevent the effect of vanishing gradient. This is the most effective solution, actually, to the problem of vanishing gradient. There are other, let me say, tricks to solve to partially alleviate the problem. One is, for example, to initialize the parameters in a way that tries to limit the negative effects. The other is to adopt an ad hoc activation function like ReLU, which tries to properly manage the variation of the gradient in the particular situations, but actually these are not really effective. So these two tricks, activation function and the modification of the parameter initialization are just small, not very effective solutions. At the end, what is actually more effective is adopting LSTM instead of recurrent neural networks, which actually need more computational power, which need more data. So it's also a problem of availability of training data, because if you don't have enough sample, these kind of approaches may incur in problems in overfitting. So these are models that try to keeping a relatively simple computational, try to model, structure the memory stage at each time step. So here you have in the standard model this simplified structure, whereas in the LSTM you have some, let me say, control blocks here, which try to retain the past information, avoiding the negative influence of the gradient in the gradient descent process. Okay, the structure and the architecture of the STM actually is not easy to present. So it's quite a long and complex. It's a long story, so it's not easy to know exactly how to properly handle this and how to properly configure this system. This is actually for this course out of the scope of our purposes. Our goal here in the deep learning tools is to, of course, exploit existing architectures like LSTM and bidirectional LSTM to solve particular NLP task, and also to compare the performance of these models, which are more traditional, with more established and more recent architectures like transformers that we will introduce later on in this course, and will be definitely more effective and efficient to solve many NLP tasks. So this will be the baseline that we will see that we will be able to beat using transformers or similar architectures. Okay, there are stages like forget, store, update. We can skip because due to the lack of time. It's not so critical, so it's not. These are not the main point of this, of course. I'm not. If you don't remember this, or if you are interested in, I can also provide additional readings about this. The goal is to selectively update the state value without avoiding the negative effect of gradient explosion or vanishing gradient. So to summarize, we have to maintain a separate style for what the input. Use some gates instead of a simplified version of the recurrent nodes. You have some nodes to. This is the most important part. So you selectively update the stages and storing negatively relevant information to avoid vanishing what is the propagated information. We will see as application, of course, of this kind of models, not only the text classification, but also other tasks. like, for example, sentiment analysis. So we will see that these kind of architectures have been applied, have been adopted to solve even complex tasks, like, for example, text generation. And we will see also what is the key, one of the key problems, which is, of course, the inherent complexity of the learning task and the inability to parallelize the computation, which will be conversely the winner, the key point, the key point of transformers, which are inherently parallelizable using the attention mechanism. We will explain this in the following lectures of this course. So here is an example of architecture. You see here the sequence of input text, the pieces of text, the inputs, and the pieces of text in the output. Again, in the encoder-decoder sequence, you have no constraint about the sequence length, neither in the input nor in the output. So you are able to natively manage variable length sequences. Okay. Okay, a few words about bias, and then we end the presentation. Let me just mention what bias is, and then maybe we can also do a quick recap at the beginning of the next lecture. But of course, this is not this is just a review. So it's not the main part of this course. So you can revise it on your own if you want more information. What is a bias? Of course, the bias is a common problem in AI. It could be related to the kind of data that you have in your source collection, like the pieces of text you use to train your model, or it could be related to the way you sample the data in order to build your own training samples, because you have to sample the data in a random way or in a pseudo-random way. And of course, the way you sample could affect the characteristics of the model, and also could affect the performance of the model with respect to specific sample or specific characteristics. In order to manage specific biases, there are architectures that are specifically designed for handling bias situations. Well, the most common case of bias is class imbalance. When you have data that are labeled differently according to, for example, the way you annotate data or the nature of the samples. For example, if you have to discover some genetic disorders which are extremely rare, it is very common to have many annotated samples of healthy patients and only very few samples of ill patients. And this is the case. This is a typical case of bias, which must be properly counteracted using neural network models. Let me just summarize you what are the categories of bias, which is the most relevant part. Okay, let's start from this. Okay, the bias could be related to interpretation, and of course you may have in your model something that is too general, which is not directly applicable to specific cases. So you try, if you take a very general and not very general purpose model, and you try to use it to draw some specific conclusions, so you of course lead to wrong or misleading conclusions. If you try to confuse correlation with causation, so if two samples are frequently occurring together, it doesn't mean that one is the cause of the other. It's not cause effect. Okay, the typical error is to use association rules to find cause effect rules. This is not the case. Rules are typically co-occurrence patterns, which means exactly only that the patterns are frequently occurring together. And then you have data-driven bias, which is a common problem. And here is the classification. The selection bias is the problem that you select data or you annotate data in a way that is not exactly suitable, natively suitable for random picking samples. If you do sampling randomly, you must make sure that the distribution of the data is suitable. For example, if you have class imbalance, like in the recognition of genetic disorders, or in hate speech detection, or in fake news detection, you are likely to incur in classification errors because the model is not specialized enough on samples that are actually fake, are actually disorders, are actually critical. Because we have too few samples with respect to abnormal cases of anomalies with respect to the normal ones. This is a selection bias. Sampling bias is also something that is more related to the collection of the data. For example, if the process of if you do a survey, you inquiry some people, mainly from a specific country, mainly of a particular gender, then you incur in errors because the population is not well stratified. Okay, you have a sampling bias. Of course, you can counteract the negative effects of sampling bias, like, for example, you can rebalance the samples using overfitting or underfitting strategies. This can be done, but this must be done only in the training phase. So do not confuse the bias mitigation strategies with the testing. So the testing must be carried out on the original test. So do not modify, do not mitigate the bias in the test. This is typical error, which is critical error from a statistical viewpoint. Okay. So I can, of course, we can deepen our exploration in how to properly handle the problems of bias and sampling in deep network, but I think it's more convenient for us to explore the domain-specific solutions. For example, when we will address text classification, we will see how to cope with text imbalances in the classes with specific solutions. So I will not present it now because it will be part of the subsequent lectures related to text classification. Okay. Any questions about bias and recurrent models? Please.
After transformers, any use, a special use that for the recurrent neural networks, I mean, performance-wise, for every usage, the transformers are better.
No, good question. Actually, there is one key problem with neural network-based approaches, which is the need of large sets of training data. This is critical for traditional recurrent models, but especially critical for transformer models, because transformers rely on a so-called pre-training and fine-tuning process, which in a nutshell means that you try to train a model on a general purpose task. You build this model you train this model on a very large, huge set of data, and then you fine-tune it to a specific task. If you don't have enough data for doing the pre-training phase, transformers do not perform properly well. So in these cases, probably RNN or like models, more traditional models, perform better than transformers even, because they do not require a pre-training stage. They just do the classical training phase. They do need a large training set, but not so large. Pre-training is something like learning, addressing we will call self-learning process, where you learn something about the data, but data means Wikipedia corpus, so a huge set of data. And this is not, in some particular problems, you don't have enough resources or enough data to accomplish this task. It's very computationally expensive. You need days of GPUs, and you need huge amounts of data. Any other questions? Okay, sorry for being a little bit late. See you on Tuesday. Have a nice evening.